We will start with the briefly revising what is this course about. So, the whole goal of statistical mechanics, it came into being with the essentially with this phenomenal paper of Maxwell who proposed the velocity distribution. Now, why Maxwell proposed the velocity distribution? Because that was the time, if you remember, around the same time the equation of state was being formulated. You remember the name of Bartholomew, Deuterici, all these names, but of course the successful one was by van der Waals. So, there was with the kinetic theory of gases, it's fair to say the atomistic view of nature which put forward by Dalton, but the atomistic view of nature came into being with the kinetic theory of gases. So, I think that is the time people started thinking, you know, to understand the perspective, that the time when people were doing classical mechanics, people were doing hydrodynamics was fully developed, almost fully developed. So, things were mostly continuum and classical mechanics based. That is what made quantum mechanics such a huge impact. So, the kinetic theory was growing, and where people like Maxwell realized that he must have realized almost much of what we know today, that the way to describe them gases, start is the simplest system as particles who are moving, colliding among themselves, colliding with the wall, and that is the way pressure comes into being, that is the way heat is being conducted, thermal conductivity or electrical conductivity. So, Maxwell went out to develop a theory of these kind of phenomena, viscosity, and he then realized that it is not possible to calculate the whole thing, but he realized one thing: if I have a distribution of velocity, probability that there is this number of particles with a velocity between v and v plus dv, which is called pv dv. When he has that kind of thing, then so the number of particles is between v and v plus dv was pv dv. That was the basic. So, pv is the probability. That was the first time in this game we are playing, the probability distribution was introduced. And he could calculate, as we know, the equation of state, at least PV equal to nRT, he could calculate pressure equal to 1/3 mc square, right, and the average speed of light at a particle which is c square is I think 3 kBt by m, other one is the speed is rho 8 by kBt, 8 kBt by pi m. All these relations that you read in your undergraduate follow from that particular ansatz, that here probabilistic description. And then, as I told you, that the difficulty was that it was difficult to take into account the collisions and the molecule. It was realized very quickly that this is system. What is beauty of this? That this system is an equilibrium. Equilibrium means it is time invariant. That means state of the system is not changing. Macroscopic state of the system is not changing with the time, but microscopic state of the system is changing with time. Okay. That the basic understanding that already was evolving at that time. And so, what Boltzmann tried to do? Boltzmann tried to put that into far more concrete with explicitly taking into interaction between atoms and molecules. And there is a term in his theory called collision cross section, where two particles come, they can come to a distance and they collide. Collision. However, the probability of collision when the two particles are approaching each other with a velocity v1 and v2, that probability is a collisional cross section which is determined by the intermolecular interaction. He could not go very far, as we discussed, and that is a subject of time dependent statistical mechanics, which we are not going to at least do this part of that, this part of the course. But it has a very paramount importance because it gave rise to a function which essentially became the entropy in a microscopic definition of entropy, which we used to discuss yesterday. So, basic idea then was is the following, that people faced with the problem of describing the such questions as why ice melts with a latent heat of 80, I think calorie per gram, calorie per gram, and why argon like systems or iron goes into FCC lattice while sodium goes into BCC, why water crystallizes to this hexagonal ice, and the hue or protein folds into the native state and why it folds into the state that it folds. So, or the how in your body when you inhale, you live in Delhi, you are all the pollution. So, you can imagine the kind of damage your DNA is made, but we still survive. The reason we survive because we have a efficient except the young children and old people immunity in our body, that all these DNA that are getting oxidized or the particles getting deposited on lungs are getting removed. Okay. So, and that thing, that the way a DNA gets continuously damaged, DNA is continuously rectified because there are certain proteins that move around DNA and correct the mutation. So, these are the processes you need to understand. So, this name of all these processes that I am talking, freezing, melting, boiling, or this protein folding, protein DNA interaction, they are called large amplitude phenomena. These are involving many particles, and as I discussed yesterday several times, that we cannot even solve with a simple potential as interaction potential, a 3-body problem. The reason Boltzmann failed beyond a point, because of that there is no way, even this time and more than 100 years now, substantially more than 100 years people have tried, and there are certain advances, but not a great deal of advances of understanding, starting from really corpuscular nature of matter, then go to calculate the thing. So, faced with the difficulties that what Boltzmann faced, Willard Gibbs decided there is other way of doing these things. This must be abandoned. This ambitious project of doing from a fully atomistic description, following the trajectory and collisions of every atoms and molecules, and by trajectory I mean that you have the two following in the first one track particles positions in the 3-dimensional space and its momentum with time, and then the same for the all other n particles. So, it is a 6 n-dimensional coordinate space which we call phase space. So, the system is executing a motion in this 6 n-dimensional, even if we neglect rotation, this huge dimensional space. So, this is called trajectory. So, the concept of trajectory is very essential, that I described before, and that will come again and again in the discussion. So, this hugely complicated thing, which is the motion in phase space, which is the trajectory, and so trajectory in phase space, that is not possible to get. Now, you think of that, say we solve the trajectory, we do that in computer simulation, trajectory of this certain number of a much smaller number. Many of the time, what do you do with that information? Yes, you know the position and atoms and molecules of every space in time for say seconds and hours. What do you do with that information? That is a huge amount of information, and much of that is just impossible to analyze. It of course correct in getting the velocity correlation function for few particles, that we know that is very helpful these days, not at the time of Gibbs, but we know can do that now. But this a huge amount of information that a trajectory has in it for equilibrium properties of the system, that information is not meaningful. Even if we have that information, it is not meaningful. So, we need a method, a system to kind of synthesize and use these information in a much more succinct and more clever and intelligent way. And that was done by Willard Gibbs with this brilliant construction of ensemble. He said, as I give the example, that there are 10 glasses or 100 glasses, you know, of water at the same half filled state, then they are all these 10, my glass has the same properties at the room temperature, same density, same specific heat, same conductivity, and every property is the same. However, each of those 10 system of this a few Avogadro number of water molecules, a few hundreds of Avogadro number of water molecules in the glasses, they are different. At any time, not only the microscopic state of water is changing in each but it is one of the way to say, okay, I want to get idea of the microscopic state, then I need to build, I have to construct mentally huge number of these glasses. Now, and each of them now at a given time, each of them are in a different microscopic state. So then he said, if I know now, if I construct just like Maxwell and Boltzmann did, a probability distribution that the system is in a given microscopic state, then I can start talking of probability distribution. So ensemble picture allowed you this transition from a trajectory based description to probability based description. That was the whole idea of ensembles. Ensembles allowed you to go to probability, and once you go to probability, then you start discussing these things in a certain analytical way which gives developed. So that was the goal, that to make the transition to the probability, and you know Boltzmann was heavily criticized for his description of probability, but on the other side of Atlantic, Willard Gibbs alone in sitting in the Yale University at the Starling Laboratory of Yale University. You can read his life in Wikipedia. I used to have in some slides his little bit about his life. He's an amazing man who alone single-handedly did all this theory of statistical mechanics. You know, and there's beautiful quotation by Mulliken and other people that you know how he single-handedly did that. Now, okay, so now what we are going to do is, so now when I started doing that, what did Willard Gibbs used? Okay, he said, I can now talk in terms of the total number of microscopic states in the system. I have the ensemble, and now I want to relate my total number of microscopic states to the thermodynamic properties. So we describe, whenever you see whatever I am saying, certain jump or inconsistency, please stop me. A class becomes better only when the students ask questions, otherwise it gets kind of monotonous. This is what we discussed yesterday. Yesterday's lecture, that this is the important thing that in certain form came from Boltzmann. And as I told you, that this could be considered very much at one more postulate of statistical mechanics or equilibrium statistical mechanics, that this is the equation from which entire equilibrium statistical mechanics was developed, that this one equation. So now, if how do you go from here to the next step? Subsequent, that means now what we need to know, we need to show that from entropy, from this equation, in terms of omega, the number of microscopic states in the system, I should be able to describe condition, like I should be able to derive an equation of state. That means I should be able to get pressure as a function of it. I should be able to get, for example, the chemical potential or free energy. So this, if I know this and I know this equation, then so this is the equation which gives the relation between the microscopic states, which is the real microscopic A of the system. We discussed in the last class that the energy level diagrams in my arrows as particles occupying different energy levels and giving rise to different arrangement of microscopic states, and total number of microscopic states we worked out with energy equal to 8, that 4 states that are allowed. If I have 4 energy levels 0, 1, 2, 3, Now with that information, see, all of them have the same energy. So all of them with the same energy, and I have this, like in a particle in a box, you have the remember, if you have worked in the particle in a box and it is done in the context of the solid state physics, that you go to density of states in omega e in a particle in a box, and that is has energy e to the power half. That means it grows exponentially, omega e, it grows exponentially with energy, and that is a very important thing. So this itself is a very important relation, but here we are saying a very fundamental thing, that this number of microscopic states uniquely determine a thermodynamic function entropy. So now, given that, I have to now discuss that from then the total number of microscopic states, how other macroscopic properties like pressure, chemical potential and follows. One important thing about microcanonical ensemble, very important thing about microcanonical ensemble, that they only are talking in terms of NVE. So this AS is the function which is NVE, and omega is a function that is of NVE. So there is no concept of temperature in this framework, microcanonical ensemble, no concept of pressure, no concept of chemical potential, nothing is there in microcanonical ensemble. So now our task is to evolve these relations to show how this thing hangs together, how the microcanonical ensemble leads us to thermodynamics. So that is the next goal, and this is the one. There are lots of equations there, and so I will not write to them. Okay, now we can start. This from the book Statistical Mechanics. So this would start. So the way we now think of this equation here, that we give a small fluctuation in the variables NVE. Now let us see what would happen. If I increase the energy, then omega will increase, right, because that you know already in particle in a box, that energy, if we increase the volume V, keeping other things constant, then again number of states will increase. Can you explain why, if I keep everything same and then increase volume V, then number of states will increase? Yeah, so best way to think of a lattice, and the lattice you develop it into a system you develop into different grids, and each molecular size you give it is a grid, and then you make it larger, keep n fixed, then there are more grids and more places to place the particle. Okay, and of course this is a dicey thing, because it is not always a monotonic function. It could be very large density, it could actually be start decreasing, but V and E it will be a monotonic function. And probably with but interacting system, at some level what will happen, you won't be able to pack it anymore. So it will go to, suddenly it will go to 0. That is the glass transition kind of scenario that we talk. Okay. So now we consider a small variation or fluctuation, and then my variation in entropy from Boltzmann formula I can write like that. Okay. There are two ways of doing it, and I will do both the two ways. Okay. ds is this is that is a variation with, so I take a derivative, partial derivative, because it is a function of 3 variables and I have 3 terms, dsd, dsdv, dsdn, dfv. Now we know this is the I call the differential form of this function, that means d equal to tds minus pdv plus mu dn as the fundamental equation or fundamental relation of thermodynamics, I think following Castellan and these people. So if this form, then from there under these conditions I can now show, so dE equal to TdS minus PdV minus mu dn, you bring the TdS on this side, then you have ds equal to, you divide everything by t. Then what you realize now, that dE ds is become t, dE dV will become minus p, dE dn is chemical potential name, right? Okay. by using the cyclic rule, which essentially ds dv into de ds dv de, this 3 product equal to -1, okay, that we use in thermodynamics constantly. Now I know that d ds equal to t, I know d dv equal to p, then I know now with combining this thing I know ds dv equal to p by t.
So why when we write let's say d by ds that equals to p, we are differentiating with respect to s, right? I mean from Euler's equation to get 5.5, we are differentiating with respect to each of the variables.
Right.
Right. So when we differentiate Euler's equation, let's say by s, you get d by ds equals to t minus d of pv by ds. So now v is constant, but what about p? Why do we not write v into pv?
No, yeah, it's a good question. Actually, this causes always this one causes confusion. You are looking at the 3 independent variables.
Yes.
The 3 independent variables are NVE. Others are dependent variable.
So that's fine, but then how do we know exactly that p does not depend on s? So if
No, p of course depend on s.
So if we differentiate that equation, then p should have.
You are talking of this equation.
No. From Euler's equation to 5.5.
Yeah,
so let's say if we differentiate with respect to s, keeping v and n constant. So you'll have d by ds equals to t minus v dp by ds plus n dp.
No, the way we are doing it, the ds at constant v and n.
Yes, but p and.
No, but p is dependent variable. This is my independent variable. My system depends on 3 variables.
Right.
That 3 variables are ev and n. So they are the independent variables. So I think I don't fully understand your question.
So what is p then? P is also a variable, right? Not an independent but a dependent one.
Yeah.
And what does p depend on then?
P dependent on all the 3. P is dependent on NVE, all 3. P is dependent on all 3 variables. The NVE, all 3. See, these are the things. So only there are 3 independent variables. System is fully determined by all 3. Okay. Everything else comes out from these 3. Okay. This is a question always asked because the question, this one comes, if we do it will come again what the question you asked. The first time I had this confusion, let me spend 1 minute on that. When we do the stability conditions in thermodynamics, there we expand the free energy in a similar form in volume and temperature. Then the way we prove that specific heat is positive. There is one proof through fluctuations, but another proof is through thermodynamics, that for a system to be mechanically stable, thermally stable, we have to say specific heat is positive, and mechanically stable, we have to show pressure is dV dP, that is negative. So these are the stability conditions. So there you expand your free energy exactly in these variables, and the exactly same conditions. Say that's the first time the confusion that you have. That I faced that confusion when I was doing. But you think a little, you have to keep track of only the independent variable. Dependent variables doesn't have. Okay. All right. So then I have, this is the equation. This is what I am saying. It is essentially the what is called fundamental relation of thermodynamics. Now, if I go back my earlier equation, so there are 2 things going parallelly. Please note, one thing that is going is that this equation, from there we are, so one is this, and then all the other thermodynamic relation we are using. However, we know that this S is kb ln omega. So, when I do these things, I do d, kb comes out dln omega de, dln omega dn plus dln omega dv. So, that immediately tells me dln omega dv will be temperature, dln omega dv will be pressure, and dln omega dn will be chemical potential. Now, these are equations of very kind of profound importance, because you are getting a definition of temperature, a microscopic definition of temperature of a system in terms of the density of states. Now, kinetic theory gives you a much simpler and exact relation between temperature. What is that? Equipartition theorem. That half mv square equal to kVt. That is the one we use computer simulation all the time. Okay. So, but you see, those things you are developed, kinetic theory of gas that way is developed in the, what we will let us see is the canonical ensemble, where temperature is given from outside. I have a system at fixed temperature, a gas of a certain number or number density and a given volume V. That we call NVT, and there I know temperature is given from outside. So, particles are undergoing collisions, they are exchanging energy, but they are exchanging energy also with the bath, and there is a temperature is maintained. In under that condition, half mv square equal to kVt. So, it is supplied from outside, but here I do not know the temperature at all. I have an isolated system, because my ensemble, microcanonical ensemble is purely isolated. It is constant N, constant V, constant A. This is something I did not emphasize yesterday. So, this is the epitome of isolated system. It is not allowed to exchange particles, N is fixed. It is not allowed to any exchange volume or become bigger or smaller, constant V by putting a certain barostat or whatever pressure, and it is completely isolated. It is not allowed to exchange energy. So, since it is completely isolated, we do not know the temperature of the system. We have no control of the temperature of the system. That is why in one second, just I'll come back. That is why in computer simulations, real though they are perfectionists, they will do all calculations in NVE, but they will start with NPT, get a constant pressure, then remove barostat. Then we will start with canonical ensemble NVT, and then they will remove the thermal bath, nose Hoover or whatever, nose Hoover thermostat and all the things, and then you simulate in the NVE. So, you simulate is this beast, and you use the conditions that we use are essentially these conditions. So, we use the fluctuation formula, but that is different. Yeah, tell me.
You were saying that it's an isolated system, so energy is not changing.
Not at all.
When you are taking the derivation, that means
yeah, this again the same question he asked. This is a huge confusion. So, this is what if you do classical mechanics Goldstein, you will see. So, I have this system NVE, then I take a small variation, I make the volume slightly bigger, slightly, very small amount, but then I study the response. Then I study the small energy, I change, I study the response, I study what I am saying by the small variations, I now study the change in omega. What I am telling, my small variation executed mathematically gives me a variation omega, and that variation is of most fundamental importance.
in simulation, if you want to carry that variation,
In simulation you cannot do, that is why we do fluctuation formula. In simulation that will be impossible to mark. Your noise will be more than what I am doing here. If you do classical mechanics, a book like Goldstein or Arnold, Goldstein devotes one full section on virtual displacement, on virtual work. This is exactly the same thing. This is a mathematical construction. We are doing a purely analytical work of at the highest level, because your thinking have to be like that. Okay. So, now that so with that isolated system, I mentally take little change of volume and I say how is omega is changing. I say okay, that gives me the pressure. and then why it goes off so quickly? So now you can see, this is what I have been telling, that from the omega, and it's a wonderful example. You will look at these equations, they are just wonderful. Total number of microscopic of this system, you make a virtual displacement in energy, and that variation is temperature. So how much the log omega will change with energy determines the temperature. Now this is we call the conjugate variables. Energy and temperature is the conjugate variable. They are connected in a mechanical, in an NVE ensemble. Now similarly pressure and volume are conjugate variable, right? And that exactly works out. I take the derivative of ln omega with respect to V, I get the pressure. And similarly, energy and number of particles they are conjugate variables, and they give you chemical potential. So this is the one. So then if you want in your microcanonical ensemble to calculate these things, we don't do it this way, but this is the way we use these three relations I give you. We use it extremely, and we will be using now in a canonical ensemble these equations to get the subsequent developments. So these are remarkable because they give our familiar thermodynamic function in terms of changes in total number of microscopic state of the NVE system. So then this is the things I told, you can write that this is the microcanonical ensemble. It's not realistic because none of the real system is NVE. Real systems typically are in chemistry is mu pt or npt. If the number of particles change, then we do the mu pt, mu is the chemical potential, p is pressure, t temperature, and many other things like phase transition. Many of the times we do npt, that means pressure, temperature, quite far from NVE. So Gibbs went on to beautifully construct, and this was, I think, the marvelous thing that he did.